Sorry for those technical difficulties. Thanks for being here. My name is Anna Kiefer, and I work at Gdal Analytics. I'm a software engineer. And we're an energy analytics startup that focuses on mapping and data analytics, and mapping the US distribution grid. And so this is data related to production, capacity, generation, and investment, as well as soft energy infrastructure, things like substations, transformers, feeder lines, things you can't just find, say, on Google or searching in Google Maps. And so I deal a lot with geospatial data, hence this talk, which is intended to be a gentle introduction to GIS and GeoDjango. So all of you probably recognize this. This is a human-readable address, and it identifies where we are right now. It's useful for humans, but it's not so useful for computers. Humans misspell things, there's formatting differences, the difference between drive and DR, for example. And so, to get around these problems, we use coordinate systems, which model a location on the Earth's surface. And they allow us to map features more easily. There are two common types of coordinate systems, geographic coordinate systems and projected coordinate systems. And geographic coordinate systems define locations on the Earth as a 3D sphere, while projected use a 2D surface, and they're better for sort of distance queries, length, area. So let's see if we can do a little bit better than this address. So this is our location in degrees, minutes, seconds, and this uses a geographic coordinate system. And it also uses what's known as World Geodetic System, 1984. And so that's a little bit better, but that's not the only geographic coordinate system we could use. This is decimal degrees, and it also uses WGS 84, and it's even simpler. But again, so this isn't the only. I mentioned geographic coordinate systems and projected coordinate systems. This is a projected coordinate system, some of you may recognize. It goes by the UTM. It uses the Universal Mercator Time, I believe. And it also uses map datum, WGS 84. First number is the grid zone designation, followed by the coordinates easting and northing, distance measurements. So the WGS 84 was invented by the Department of Defense. But they invented other ones as well, them and other organizations. And so this is the military grid reference system, and it's used by NATO militaries. But that's not the only one. There's the state plane coordinate system, which divides the US into 124 geographic zones. But that's not the only one as well. Because we're in the US, we should probably use feet, not the metric system. So that's in feet, but there's also something known as the international foot, which is not equal to the US survey foot. So this is a representation in terms of the US survey foot. But there's additional ones. This is the Maidenhead reference. That's the Maidenhead reference system. It's used by amateur radio operators around the world. And finally, or no, not finally, sorry. This is a different global area reference system developed. Finally, this is what I found actually yesterday. It's called What 3 Words, and it tries to take all of our points on Earth and give them 3 words. And this is where we are right now. Dozed feels unity, which I take to mean we're all tired. And so all of these are valid ways of representing our location. But as you can see, they're all different formats. And so we need to get this into a standard format. And I basically mention these to show you all of the different coordinate reference systems there are, and the importance of standardizing our data, and how GeoDjango and PostGIS uses these and turns them into standardized while still being flexible. So the next time one of your friends asks you where you live, use one of these other reference systems. Okay, so for those of you unfamiliar, GeoDjango is Django's robust framework for handling geospatial data. It gives developers the ability to store geospatial data, query, aggregate, and filter it. And it provides support for 4 spatial database backends: Postgres, SQLite, MySQL, and Oracle. And Postgres and SQLite are in bold because it offers most support for those 2. And even amongst those 2, Postgres and PostGIS have the most support. Don't fight me on this, but I think SpatialLite and SQLite has some limited support for some geospatial functions that are common. So I'll be using Postgres. This is Postgres plus the Earth equals PostGIS. Okay, so now how to discuss how PostGIS deals with all of those coordinate systems that we saw in our last slide. Okay, so for those of you who have used geospatial data, this might look familiar to you. This is known as the SRID, what's a spatial reference identifier. The SRID defines what coordinate system you would like to use. Now, there are many SRIDs, hundreds, and they're used for different geographies around the world. But to perform geospatial functions on the same data, it has to be of the same SRID. So this defining your own SRID could be good if all of your data is, say, in one state or in one small geography. But oftentimes, it's not. So PostGIS offers the ability, it sort of throws it has the ability to put in unique SRIDs, but it sort of recommends that you use SRID 4326, and that maps to the WGS84, which I mentioned earlier. And then when you need to measure something like area, distance, or length, you use a function to create that column, and then in your projected coordinate system, and measure it that way. Okay, so now I want to just discuss a little bit of sort of GeoDjango data models, which look surprisingly similar to the regular data models, except there's one spatial field type, and that's the point, line string, polygon, or multi-point. Not circles, though. Circles, it turns out, are much more difficult and complicated than you thought in elementary school. So you don't define circles, you define them as polygons. And GeoDjango also has support for raster data, which I'll get to in a little bit. And then, as I mentioned, you can put in an SRID or use the default, which is 4326. A lot of mapping frameworks and user-facing use coordinates in lat-long order, but that's actually incorrect. Well, according to PostGIS, it needs to be in XY order, which would be longitude, latitude. So the very first application I developed, I did not know this, and all of my points turned up, I think, in Asia somewhere. So, okay, and then these can be initialized using WKT, WKB, hexadecimal, or geojson. And so this all looks well and good, but as I was thinking when I first started, wait, what the heck is WKT? I didn't know anything about what WKT was. So this is just a representation of WKT. WKT stands for well-known text, and it's a text markup language defined by the Open Geospatial Consortium, of which the US Department of Defense is a part of, and many other, 500 other government institutions. And it shows beneath it its binary equivalent, and that's how the data is actually stored in the database. All right, so now that we have a better understanding of what these data formats are, we can tackle what I mentioned in the last slide, the differences between vector and raster data as it relates to GIS. Okay, so on the left we have raster data, and this is represented by largely satellite imagery. A raster consists of a matrix of cells or pixels organized into rows or X and Y columns, where each cell contains a value of information. And this is good for representing continuous data, real-world phenomena like temperature, elevation, or other spectral data, continuous data. And vector data, on the other hand, is good for representing geometries. And all vector data consists of a list of coordinates that define vertices. So again, it's points, lines, and polygons, and that is usually small storage requirements whereas raster data has large storage requirements. And so that is a polygon representing the county of San Diego. Okay, and so here are the steps. They look remarkably like setting up a regular Django model. You get or create your geospatial data somehow. You create your Django model as you would, defining your SRID and your geospatial field, point, line, polygon, etc. You find some way to import your data, and then you can start querying. And there's a ton of different querying methods that are really fun. You can perform data discovery, min, max. You've got a bounding box, area, and length. And you can query and filter similar to the way you would, as usual, querying using Django's ORM. It comes with contains, within, intersects, borders, overlaps, touches, tons, and you'll need to look up the documentation, as I did, probably many times, to figure out the differences between some of these. And then you can aggregate data based on filters and create new geometries using unary union, or cascaded union, which can merge lines, polygons, and multi-polygons, and lines, polygons, and points. Okay, and now just to go over some other popular libraries that I use a lot. I use Shapely, which is good for vector geometries, GeoPandas as well, which is good for vector geometries, and Rasterio, which I don't have much experience with, but I have heard it's really popular to manipulate raster data. Okay, so far we've covered on all of these things. GeoDjango supported geography field types, or geospatial field types, different coordinate systems projected versus geographic, raster vector data, distance and spatial querying methods, and data formats and data translations. So, are we all done? No. We haven't discussed one important aspect that I've spent a lot of time on, and that's debugging and troubleshooting. Okay. So, some of these geospatial libraries can be frustrating, incredibly frustrating, especially when you're doing really complex geospatial analyses. I've often received geometry and topology exceptions that are difficult to debug, Gdal being one of them, notorious for having different versioning issues. I don't know if the creator of Gdal is here, but I love Gdal, but it can have some issues. And so, for example, here's one that I just want to touch on. So you can see above, I have geojson with a multi-polygon, and it's an empty, there's empty list as its coordinates. And I'm able to initialize my geos geometry, and when I print its well-known text, it comes out empty, but the valid method comes out true, and that's because GeoDjango is not validating that there are actual polygons within my multi-polygon. And this is different to the below block, which shows I'm trying to instantiate a polygon, and that is an empty geometry, an empty list. And then I get a Gdal error that says, basically invalid geometry pointer, you can't instantiate a polygon with an empty list. And so this showed up. I imported for hours a lot of multi-polygons. It turns out they were empty. And I thought they were valid, because I was printing is valid, or in this, so I was printing valid, and it was turning out okay. So that's just one issue that I've come across. So I've compiled a hopefully helpful list of tips to debug. Okay, so despite the example I just gave, I do think that the valid method and Shapely's is valid method are really useful for figuring out whether or not a polygon is valid. If it's a line and there's a break in it, I believe is valid will return false. It'll validate whether or not polygons are entirely closed. And then when in doubt, plot it using QGIS. I mentioned that app before that I was working on. I was trying to plot the US landfills in the US. And they weren't appearing on my map at all. And I realized that a lot of them were in the Pacific Ocean, which might be valid, but was not where I wanted them to be. So it helps to plot them using free software, QGIS being one of them. Also, plotting them helps discover slivers in between features, maybe holes in polygons, or breaks in lines. Oftentimes, these will import smoothly, but you'll get errors down the line when querying them. And so I found that very helpful. Other things are memory and performance issues that I've come across. I came upon this the other day. One of my geospatial queries was taking hours, and I realized that the M was actually miles and not meters. Somewhere along the line, I must have transformed it into miles. And that was causing a lot of the other geometries around it to be contained in the filter. And so make sure you have your units correct. And then there's also a helpful simplify method that you can use. And this, you can add a tolerance decimal, that's between 1 and 0, and that simplifies the coordinates. So it'll cut out some of the coordinates, and depending on the precision needed in your app, that can be very helpful and speed up queries. Finally, the prepared also does something similar. It prepares it for more efficient geospatial analysis. And then, some of you might be familiar with this, there's something called the right-hand rule. And that basically says that all of the interior coordinates need to go in a certain direction. They need to go clockwise, and the exterior need to go counterclockwise. And this has resulted in a lot of Gdal errors that I've spent a lot of time trying to debug. Okay, so I'm going to give a short demo. This is the app, one of the apps that I've worked on, and I just think it shows how we've used PostGIS and GeoDjango. Let's see if I can. Sorry, I should have had this up before. And it's our app called Grid Assessor, and it maps US distribution data. Okay, so here's the US, and actually I'm going to just go ahead and search. I think I've got that correct. This is our location where we are currently. At the Marriott, there we go. There's some nice reverse geocoding going on. All right, and so the the orange are feeder systems around us. The yellow are transmission lines, and then land parcels will start to come in, and those are polygons. Or the polygons will start to come in, and those are land parcels, excuse me. And so you can see we've used polygons, multi-line strings, and points to represent where we are in the energy around us. All right, so now, I'm not going to click around too much, just wanted to, just show that. Oh no, I lost the presentation. All the way left? Nope. There we go. Oh, I see, I need to go back. Well, I think the last, okay, well, I think the last slide is just thank you. What's up? Oh, it'll go back? Oh, there we go. Thank you. Sorry. All right, there we go. My last slide. Thank you all so much for staying till 5 p.m. This has been really fun. And yeah, thank you to the DjangoCon community and all of you.